Yeah, I'm Sushant, and this is Pritpal. We actually have Tony here as well, but our last co-founder Keegan's still at the booth.
All right. So please go ahead.
All right. Hey, so yeah, as I said, I'm Sushant. This is Pritpal, two of the co-founders of Enpact, and we're here to present a self-powered pressure mapping insole for orthotic treatment. So I'm going to quickly first just go over our team, which forms Enpact, and that forms from Tony, who is our lead electrical and hardware engineer. Me and Keegan, who's not here, are our lead on the materials and manufacturing side, and Pritpal has been our research lead. So to go over the agenda that we're going to present to you, I'll quickly go over what motivates us, what motivated us to form Enpact, and then how we made our solution, what materials and circuitry and software was involved. Then we'll go over some of the tests we did and the verification. All right, so first of all, what are foot orthotics? So these are custom molds that you get prescribed by a pedorthic doctor that help reduce unnecessary stresses or strains in not only your feet, but it could be your lower back or your upper legs. So over time, as you walk over these are usually insoles. They correct your abnormal or irregular walking patterns. But what is the problem with these orthotics currently? There's no current way for foot doctors or pedorthists to quantitatively talk with the patient and assess whether a manufactured orthotic is effective. So what I mean by that is answers such as, was the orthotic manufactured perfectly correctly? Is it supporting the patient's foot everywhere from every angle? These answers don't get answered very well. Or things like, when does the patient need to get a new orthotic? Because over time, the patient's feet will conform to the orthotic. So the doctors do have what are called force plates available for orthotic prescriptions, but they have certain problems. There are these huge plates which are not portable, they're expensive. The patient can only get very limited data off that because they either just step on it and step off or walk over it once. There's no continuous data recording using these force plates. And the most important part is you can't use these once the orthotic has been manufactured. So once a patient gets an orthotic, you can't use these force plates to see if the orthotic is being effective. So about 1 in 10 orthotic patients actually go back to their doctor and say, hey, there's this specific part of my heel or toe that I'm having a problem with. There's too sharp of a pain. It's really difficult to verbally, quantitatively tell the doctor where they're having a problem. And more likely than not, if they get their orthotic remade, it's going to be expensive, it'll take a long time, and they'll end up just being more problems than before. So there's no good quantitative way to measure the quality of a manufactured orthotic. And our co-founder, Keegan, can attest to this. He's had orthotics for about 10 years now. So what have we done to solve this issue? We've created a pressure mapping smart insole, and this thing has an array of sensors inside it, which are triboelectric sensors, and we'll talk about how triboelectricity works in a moment. These essentially generate voltage upon pressure. So as you're walking or running or stepping on it, these will generate their own power, and that's why they are self-powered. As the patient is using this with their orthotic, it will communicate the data wirelessly via Bluetooth to their phone or tablet. And essentially the plan is for the doctors to actually own these insoles, not the patient. So the doctors will give these out with the orthotic to the patient. The idea is the patient will use it for, let's say, a few hours or a day and walk with it and collect data over time. And when they go back to the doctor, they can give them a nice foot pressure map that's averaged over time, and the doctor can quantitatively see where they're having an issue in their feet, where they're applying a lot of pressure, where they're applying too little pressure, and they can combine this by visually seeing how they're walking and where they're having pain. So this can help to quantitatively assess the effectiveness of a manufactured orthotic. So in a bit, we will show you a quick demo of how exactly this orthotic works and what exactly the patient and doctor will be seeing in real time. But before that, let me get into some of the material design. So our sensors, there were 7 sensors in the previous image. If you remember, they're essentially just little squares. Very simple, easy to make with just thin film materials using Capstone as the backbone and Teflon and copper as the contact materials. So this works on the basis of triboelectricity, which is basically contact electrification. It's very similar to static electricity, like rubbing a balloon over your head. In this case, when Teflon and copper come into contact, when you press your foot on the insole, it will transfer charges, electrons from the Teflon to the copper. And as it's separating, it will create a current going back the other way. I'll explain this in the diagram soon in the next slide. But basically, on the triboelectric series, we've chosen to use copper and Teflon. We did also try to use aluminum to create a bigger difference in the triboelectric cities, which would give us a higher voltage. But we realized we didn't need that much of a voltage impulse. And for other reasons, such as ease of soldering, we decided to use copper and Teflon. So to quickly go over how each of these sensors work, as I said, once they come into contact at the top, the copper will transfer its electrons to the Teflon, because Teflon is more electronegative. And once you start to separate this as your foot goes above, or your foot is not touching the insole at that particular point, as they separate, current will actually flow from the bottom electrode to the top electrode to neutralize the charge. And every time, and this becomes a cycle, every time you're pressing and compressing these sensors, you're getting charges flowing in the positive and negative direction. So you actually end up with an AC current. And you can see that in the graph on the top there. So every time you're pressing on it, you're actually getting a positive voltage spike. And every time, if your foot is not touching it or you're lifting your foot, you're going to get a negative voltage spike. We're going to use actually, Pritpal will talk about how we actually convert that to a DC signal in a bit. But this is essentially the simple basis sort of contact electrification in which each of our sensors work.
So after the material design, the next logical step is to design the circuit, and while meeting 2 key circuit design requirements. So the first circuit design requirement is to accurately and reliably detect TEG actuation. And this is important because this minimizes the amount of post-processing needed to determine when the TEG is actually actuated and how much pressure or force is applied to the sensor. The second requirement is to ensure compatibility with a variety of analog to digital converters of different microcontrollers. And this is enabled by converting a bipolar, so positive and negative signals, to just unipolar or just positive signals, as most common analog to digital converters only really take unipolar signals. So this is a schematic of the circuit design. It is relatively simple. You have the TEG sensor array that is connected in parallel to 100 nanofarad capacitors. And the capacitors are then connected each to a pin on the analog to digital converter on the NRF52 BLE microcontroller. Then the digital signals are then sent to the radio via low energy Bluetooth communication to the mobile application. So we meet these design requirements from mostly from the parallel configuration of the capacitors. And to really reinforce this is to look at the voltage characteristic that we see on the right. So again, with the resistive load, we have a positive voltage spike corresponding to the compression and a negative voltage spike corresponding to the separation. With the capacitive load, however, as you're compressing the sensor, the TEG sensor actually pushes charges onto the capacitor, thus increasing the capacitor voltage. And when you're separating the sensor or releasing your foot off the sensor, this actually results in the charges draining from the capacitor. So you get this nice bipolar to unipolar conversion, and this can actually use to kind of detect how much TEG is actually being actuated, and the pressure and force mapping that I'll talk about a little bit later as well. And so essentially the capacitor is essentially like integrating this AC circuit. In addition to the circuit design, we also had to design the firmware, and the 3 design requirements include periodically sampling the voltage from the capacitor bank, implementing a BLE interface to connect with the mobile device, and real-time data transferring to your mobile device. And real-time basically means that when you apply pressure onto the sensor, what we see on the mobile application is almost an instantaneous response. So the center, the NRF52, is kind of where the firmware is, and it kind of acts like an interface or a bridge between the information from the capacitor bank and the mobile device. So the firmware can be kind of broken or grouped into 2 blocks, the application logic block and the BLE stack block. The application logic block is mainly used to periodically sample the information from the capacitor, and the rate at which this is sampling is actually pre-programmed in the firmware. The BLE stack can be kind of thought of as these software and electronic components that basically implement a standardized protocol for communication in Bluetooth, essentially repackaging your information that is coming from the hardware to something that is more easier to read in terms of software. So the application logic addresses the first requirement of periodically sampling the voltages from the capacitor bank. Again, as the sampling rate is determined or pre-programmed in the firmware, and the second and third requirements are addressed from the BLE stack block that implements the BLE interface that we want to connect with the mobile device, and also enables this real-time data transferring to the mobile device as well. So in terms of the verification tests, we wanted to verify the capacitor voltage characteristic that we showed before, and we wanted to verify this force response of each sensor. So to verify the capacitor voltage characteristic, we basically just actuated the TEG sensor and sampled the capacitor voltage at a rate of 30 hertz. And to verify the response of the TEG cell, we simply just loaded the cell with different weights, and we just looked at the capacitor voltage that we read out. So here are the results for the first verification test. And so we get the characteristic that we want. So basically what this means is there's minimal post-processing in the software end to determine when the TEG is compressed or separated. So you have the curve that we kind of showed previously. As you compress the TEG sensor, you're increasing the voltage, and as you're separating it, you're decreasing the voltage as you're pulling charges away from the capacitor. And here is the results of the second verification test, where we just place different weights, and we see that there's a nice correlation between the voltage change and the force or pressure applied to the sensor, which makes it so we have this kind of voltage mapping for each sensor. So in post-processing, it's very easy to say, like, okay, like if we have more voltage that we're reading, we have more pressure being applied to each sensor. So kind of bringing that all together, the circuit design, the material design, and the firmware design, here is our prototype. Here's a quick video that cannot be played. Oh, okay, it's playing. So as you apply, force or step on the insole, you get the nice pressure map of your foot on the mobile application. So yeah, that's our final prototype. And to end off, our prototype right now is not perfect. There are some things we can improve on. First, we can increase the density of the TEG sensors. This enables this continuous pressure mapping that is ideal, because right now we have a very discrete type of pressure mapping. We can also Related to the continuous pressure mapping, we can also fabricate sensors onto one Capstone backbone, and this results in kind of coupling of sensors, which is also kind of, we need a certain amount of coupling between sensors to get this, again, continuous pressure profile. But the trade-off is that wire management, increasingly becomes an issue, but a potential solution could be maybe printing traces, conductive traces on the Capstone backbone. And then we can also introduce surface modifications on the two materials that are coming in contact to increase the force range of the sensing to upwards to 500 newtons. And then our final area of improvement could be obviously miniaturizing the electronics via some sort of PCB design to decrease the form factor and just overall make it look nicer and prettier. So yeah, that is the end of this presentation. We'll be taking questions. Thank you for listening.
Thank you very much. Very nice job. Questions first from the judges. How you are power the data transmission unit?
Yeah, so there's a battery actually powering the data transfer. We couldn't generate enough power to actually do both.
So you're using a battery.
Yeah, there's still a battery for the communication.
What's
Yeah.
the kind of batteries you use?
The
Coin cell, just the
Coin cell.
CR232.
So it can still be embedded in this.
Right, yeah. And I guess the fact that the TEG sensors are self-powered is that it prolongs the battery life, right? Because you don't need to feed external power into
Yeah.
the sensors to read off of it.
Oh, use my.
Oh, okay. But yeah, so yeah, the battery life is prolonged by having the sensors as self-powered.
But you also design the transmission unit yourself, or you?
So the Bluetooth stack, as Pritpal mentioned earlier, it comes with this part of the Bluetooth chip, and that like the protocol standardization is all handled by a pre-built package that they provide the software developers. So all we had to do was write the firmware that does the application logic, and then feed the data into the Bluetooth stack, which is a pre-built component. Yeah. And the semiconductor is already pre-built too. So.
You have this 7 sensors on this board. Why choose 7? Or is it
Right.
So right now, in order to cover, our first prototype was meant to cover the entire area of the foot, and our sensors are a certain size of square right now because of how much power we need, how much surface area we need to get enough of an impulse to get like a on and off or like force characterization. So we have tried to miniaturize our sort of sensor squares so that we can fit more of them in there, but we have tried things like nano modifications. So far, we haven't had a huge improvement with them, and that's why our size is limited to, let's say, the 3 by 3 centimeter squares we're using right now. That's why we were able to fit 7 of them. But eventually, the plan is to try and miniaturize them.
Also on the Bluetooth microcontroller, there's only 8 analog to digital conversion pins, so maximum of 8. But because the squares are a certain size, we just fit 7. Yeah, so if we wanted more, we'll have to do multiplexing to multiplex, let's say, 64 signals into 8 pins. But yeah, for the future, that's something we need to improve on, is to multiplex a lot more signals into 8 analog to digital converter interfaces. You would just get a better resolution of the mapping, right? Because you can see more finely where the pressures are being applied. Because right now, the 7 circles, if you kind of touch anywhere around that circular area, you would get a hit. But if you had a much finely divided array, then you would get more detailed mapping.
What's envisioned as the next step? Because this is mapping. You would still have to pass that back to somebody to make it
So this, yeah, so the idea is for like these doctors to kind of have like the orthotic and then maybe this insole or this layer of sensing on top of it. So that's what the idea is. So we don't. So like integrating the sensors onto the orthotic, is that the? Okay. All right, thank you.